1.2 Computing limits. In this section we're going to find limits using all sorts of different techniques, algebraic mostly. We're also going to figure out what a limit is by looking at a graph. We'll start off with some basic limits. Got a picture that goes with each one of these. The limit as x approaches a of any constant is just equal to that constant. You can see that on the graph down below. As x gets closer to point A, y gets closer to that constant value, because y is always that constant value. Next graph says limit as x approaches a of x equals a. As x gets closer to a, y also gets closer to a, because of the nature of the graph y equals x. Part C is a little trickier. It says limit as x approaches 0 from the left. A little minus sign there. That means we're looking at the graph of y equals 1 over x. And we want to get close to 0 on the left-hand side. Y gets close to negative infinity. If we look at the same graph, we get close to x on the right-hand side. Y looks like it's going up real high, so we see when as x approaches 0 from the right is positive infinity. And that notation is kind of important. That little plus sign that looks like an exponent is really saying get close to that number on the right-hand side. Just like if we see that same notation with the minus sign, that means we're getting close to x on the left-hand side. If we don't see the plus or the minus, that means we have to look at both sides. And if both sides don't match up, we say the limit does not exist. In parts A and B, both sides matched up. On part C, the left went to negative infinity, but the right went to positive infinity. So if I were to ask myself this question, limit as x approaches 0, or 1 over x, since the left and the right don't match up, we say it does not exist. In example 1, we're just illustrating that part A from the previous slide. We've got the constant function y equals 3. You should be able to imagine what that graph looks like. No matter whether x is negative 25, 0, or pi, as x gets close to any of those numbers, y is always equal to 3, so it's safe to say that y gets close to 3. Example 2 takes a look at the function y equals x, and as x gets close to 0, y gets close to 0. X gets close to negative 2, y gets close to negative 2, and so on. This next example kind of explains the y equals 1 over x situation that we saw in parts C and D of that slide. We should know that as x gets closer and closer to 0, think of a number like 1 divided by 0.00001. That's really asking how many times does 0.00001 go into 1? And the answer? A lot. That's why as we get a number close to 0 on the bottom, but positive, we say that is infinity. The closer you get to 0, the more times that goes into 1. And if we get close to 0 on the left, it means we have a tiny negative number on the bottom. Positive divided by negative is now a negative. This first theorem of the section talks about two functions, each having a limit that exists. And it tells us ways to break this down into something easier. It says if we've got two limits that exist, and we want to add up those limits, we can just find the limit of each one separately and add those up. Same thing works for subtraction. If we're finding the difference of two functions where the limit already exists, we can just find the limit of each one and subtract them. Same thing works for multiplication and division. The only place you have to be careful there is you can't have the limit on the bottom equal to 0, because we can't divide by 0. And it works for radicals also. But you have to make sure that if you have an nth root that's even, for instance, a fourth root, its inside has to be positive or the limit does not exist. Those same 5 rules are summarized in words down below. And look over those, make sure they make sense before you move on. This next example just illustrates some of that last theorem. Looks like we've got a function that's asking us to find the limit of 3 functions added and subtracted together. To make that easier, we just split it up into 3 limits. In fact, we could factor that 2 out because it's constant. Then it's normally easier to find each individual limit separately. Same thing works with multiplication. A limit as x approaches a of 3 functions, all multiplied together. We can just find the limit of each one separately and multiply our answers. And the same idea works for exponents. We want the limit as x approaches a of some function cubed. We can just find the limit as x approaches a of that function and then cube our answer. So in other words, limits really work out nicely. They do what you want them to do for the most part. So let's actually figure out a limit here. You might remember from pre-calculus that direct substitution works as long as it's a nice function. I'm using air quotations when I say a nice function. Typically, if you can plug a number in, that's going to give you the limit. If you can't plug the number in, that's when we're going to see some of the harder problems, and that comes later. In this particular case, we can plug the number in. It's called direct substitution. And this really is a result of all those theorems we just saw. It says we can take each of these 3 pieces separately and find the limit of each one on its own. And it ends up being just this thing we call direct substitution. Order of operations is going to help you simplify. And we move on with our life. This next theorem basically says that direct substitution is going to work always on polynomials, which we kind of already know because, as I explained, if you can plug in a number, you're allowed to plug in that number for a limit. That's how direct substitution works. If you try direct substitution and you get something like division by 0, that's when we're going to have more of an issue. Example 6, this is a polynomial. We're not actually going to figure out what this is expanded to the 35th power. That would definitely be DTM, doing too much. But we can try direct substitution. Maybe you should pause the video and try that on your own, see if you get the same answer I did. And that's it. So now we've got this rational function, but it's just really a bunch of functions that we already know how to find the limit for, all put into one big function. Because this is a division of 2 polynomials, we should be able to find the limit using direct substitution, unless it causes us to divide by 0. So that's the first thing I would check. Plugging in the 2, see if that causes us to divide by 0. And it doesn't, so we can just try the direct substitution. Pause the video, try that on your own, see if you get the same thing I did. And that's it. Now we've got some trickier issues. Notice on all 3 of these we've got a 4. If I try direct substituting 4, I'm going to get division by 0 in all 3 cases. So direct substitution is out. Instead, our A says approach 4 from the right. So let's think about what that looks like. 2 minus 4 from the right over 4 from the right minus 4, 4 from the right plus 2. The only place this from the right part really matters is when we're close to 0. 2 minus 4 from the right is going to still be negative 2. It's going to be real close to negative 2. 4 from the right plus 2 is still going to be 6. It's really that 4 from the right minus 4 that matters. You should be thinking of a number slightly bigger than 4 minus 4. It's going to give you a number close to 0, but what's important is to realize that number is close to 0 and positive. The reason that's important, we now have on the bottom 0 from the right times 6 would be 0 from the right. And you should be able to look at that as negative 2 over 0 from the right must be close to negative infinity. We're doing negative divided by a positive. Go ahead and pause the video and try part B and then part C on your own. Just try part B right now. See if you get the same thing I get. Very similar process this time, except this time I get a negative divided by a negative. So I get positive infinity. Part C, you don't really have to do all that work again. You have to look at the limit from the left, look at the limit from the right. If they match up, that's the answer to part C. If they don't match up, you say does not exist. And this time, the left and the right limits do not match up, so we're done. Next up, we have 3 more functions where when we plug in the numbers using direct substitution, we get division by 0. One of the techniques of finding limits is simplify your function before you try direct substitution. And we can factor something out maybe, and it'll fix the issue. For instance, in part A, we can't plug in 3 because we divide by 0. However, if we factor the top, we can cancel out one of the x minus 3's, and now direct substitution works. It's worth noting that the limit and the function value itself, if I were to figure out f of 3, I don't necessarily get the same thing. If I plug f of 3 back into this original equation, I get undefined. What that really is going to mean is that there is a hole in the graph. You might remember back in pre-cal when we graphed something like this, we had a hole at x equals 3 because the factors canceled out. Anytime you have something cancel out like that in a rational function, it's probably because you had a hole right there. The limit value and the function value did not match up. One was 0, one was undefined. So if I were to ask you on a quiz or a test, what is the limit as x approaches 3, you'd say 0. If I asked you what is the function value at 3, I'd say undefined. Later on in the chapter, we're going to find out what it's called when the limit value and the function value match up. There's a special word for that. It's called continuous, but we don't have to worry about that right now. Right now, go ahead and pause the video and try a similar process for parts B and C. See if you can get through them okay. Just worry about the limits. Don't worry about the function values. The odds are that both of these function values are going to be undefined anyhow. Part B worked out very similar to part A. Should have gotten negative 2 over 7. Part C is a little trickier. I did my factoring, I did my canceling, and I still end up with 7 divided by 0. When that happens, we have to look a little more closely. We have to look at the limit from the left and the right. Except I wrote right and left. Either way, you have to look at both sides of what's left. If these two left and right hand limits match up, then our limit exists. If these don't match up, we've got a problem. And after a little bit of investigation, we can see we get 7 over 0 from the right, 7 over 0 from the left. One of these is going to give us positive infinity. One's going to give us negative infinity. They don't match up. So our final conclusion is this limit does not exist. It's worth noting, just because you get 0 on the bottom does not mean the limit will not exist. We haven't seen one yet where the limit does exist, so let me make up my own real quick. If we saw something like this, limit as x approaches 0 of 1 over x squared. Let's see what this one looks like. If we just plug in 0, we have an issue. So we're going to go from the right, and we're going to go from the left. When you square a positive number, you end up with a positive number. When you square a negative number, you get a positive number. This time, both limits matched up. So we can say in our conclusion that the limit was infinity. So you don't always get just does not exist. You don't always get positive infinity and negative infinity. Graphically, this guy looks something like this if you don't remember. And as we get close to 0 on the x-axis, our y values get close to infinity. This next theorem tells us that if we've got some rational function and the bottom does not equal 0, then it's nice. We can use direct substitution. Then it tells us if the bottom is 0, but the top's not, then the limit does not exist. We say does not exist even if the limit really turns out to be infinity or negative infinity. That's still classified as does not exist because those aren't actual numbers. We can still think of the idea of infinity and negative infinity, but it would also be right in those cases to say the limit does not exist. That being said, if your limit is infinity or negative infinity, you should still be aware of that because it's a useful idea. So now let's talk about some radical functions. So try plugging in one using direct substitution, and immediately it doesn't work, of course, because nothing's ever nice, right? You remember from honors pre-cal, the way we're going to handle this one is multiplying by a special thing. Take a second and think about it. If you thought conjugate, pat yourself on the back and give yourself a cookie. This is going to make things work out nice, as you'll see. Go ahead and pause the video and try to figure out the next step on your own, just to practice that multiplying by a conjugate. The bottom is the part that you really want to be careful with. Multiply square root of x times square root of x, we get x. Outside and inside are going to cancel. That's always what happens with conjugates. And then negative 1 times positive 1 is negative 1. Look at the beautiful thing that happens now. Cancels out. Now we get to try direct substitution again, which of course works this time. Plug in 1. We get our answer, and we move on with our life. Next, we're going to find limits of a piecewise function. I've given you this function in both graphical and algebraic form. We should be able to find the limits either way. So I'm going to cover up the graph first. And talk about this problem just from the viewpoint of the algebraic function. First thing it wants is a limit as x approaches negative 2. To figure that out, we've got to find the limit as x approaches negative 2 from the right and the left. On the right-hand side, that means we want numbers slightly bigger than 2. So we have to look at this first interval, and we can use our direct substitution. 2 squared is 4, minus 5 is negative 1. Negative 2 on the left, that means we want numbers slightly smaller than 2. So I'm going to look at this piece of the piecewise function. And when I plug that in, I get 1 over 0. Slightly bigger than negative 2. Just 1, 0 from the left, which definitely does not give us negative 1. So for limit as x approaches negative 2, we should say does not exist. Next up, we look at 0. We have to look at 0 from the right, 0 from the left. Notice that numbers slightly bigger than 0 and numbers slightly smaller than 0 both fall into the middle piece. So I don't have to actually look at left and right because it's going to be the same on both. Both are going to use the x squared minus 5. We get negative 5. Since they match up, we say the limit here on part B is negative 5. In part C, we're going to look at x approaching 3 from the right and the left. When we want from the right, we've got to look for numbers slightly bigger than 3. So right there. And we can use direct substitution. 3 plus 13 is 16. Square root of 16 is 4. Oops. Then we want 3 from the left. Numbers slightly smaller than 3, which is this middle piece. Plugging 3 there, we get 9 minus 5, 4. The two limits matched up, so we say 4. Let's look at this graphically now. As x gets close to negative 2, we look on the x-axis close to negative 2, notice one side goes down here, the other side goes down to negative infinity. That matches our negative 1 and negative infinity that we saw algebraically. Part B says let's get close to 0. So if we get close to 0 on both sides, notice both sides go straight down to that negative 5, which is what we saw algebraically. And lastly, looking as we approach 4, looking as we approach 3, from either side, both sides look like they go right up to that point, and that point is y equals 4. That's it. Go ahead and do your guided practice. Come in with some good questions, and I hope you learned a lot.